Okay. Şimdi çok şükür ki bu dersin acılı kısmı bitti. Yani benim için en acılı kısımlar genellikle Nyquist, body plot, işte phase lead lag design'lar. Yani gerçekten bunları anlatırken çok zorlanıyorum. Neyse ki bu kısımlar bitti. Şimdi de hiç böyle acısız kısımları var. Yani state space kısımları da oraya geldik mi artık ben böyle iyice bir rahatlarım. State space kısmında. Çünkü her şey genellikle straightforward o kısımda ve fikirlerin anlaşılması çok zor değil. Ve de işin güzeli time domain'deyiz. Yani frekans domain'de işler bir anda non-intuitive hale gelebiliyor ama hala time domain'de kalan bir şeyler olduğu için. Şimdi nereye kadar geldik sizce kontrolde? 1800 değil. Bereket 1800 değil. Nereye kadar gelmiş olabiliriz? Root locus 1950 arkadaşlar. Root locus. İşte Nyquist 60'lar falan desek. State Space'de bizi 70'lere getirecek. 70-80'ler arasına getirecek. Eğer bir yerde modern kontrol ismini duyarsanız şunu hatırlayın. Bir şeye modern demek son derece salak bir durum. Çünkü şimdi artık State Space'e modern kontrol denmiş. Hatta Ogata'nın kitabının ismi bile Modern Control Engineering'tir. Bu şu demek State Space'te anlatıyoruz aslında. Ama gördüğünüz gibi 1980'lerde kalmış bir yöntemler aslında. Şimdi bu dersin amacı birazcık şu. 1980'lerden itibaren eğer kontrol çalıştığınız takdirde. Şimdi ne olmuş? İlk önce root locus'la Laplace domain'de başlanmış işler. Ondan sonra Nyquist'le frequency domain'e geçmiş. Ondan sonra modern kontrol dönemi gelmiş. Modern kontrol dönemi tekrar time domain'e geçiyor. Yani her şey artık time domain. Özellikle multiple input, multiple output sistemlerde modern kontrol dışında kullanabileceğiniz şey çok az. Sonra tekrar bu maalesef 80'lerden 90'lardan sonra tekrar frequency domain'e kaymaya başlıyor. Yani eğer 90'lardaki veya 2000'lerin başındaki kontrolle ilgili şeyler yapmak isterseniz işte H-infinity kontrol, robust kontrol filan diye alanlar çıkmış. Bunlar tamamıyla frequency domain'de geçiyor. Esasında dersin başında söylediğim işte Nyquist'i çıkaralım mı, çıkarmayalım mı? Şimdi yani bence kontrol çalışmak isteyenler için mutlaka bilinmesi gereken bir şey ama genel bir audience için bence çok gerekli şeyler değil. Ama işte çıkartamamamızın sebebi en azından bir kısmınıza da Nyquist öğretmiş olalım kontrol çalışacak olan veya ilgili alanlarda çalışacak olanlara. Frequency, evet.
Kontrolü yüksek yapan birisi ben Nyquist bilmiyorum diye nasıl diyeyim?
Şöyle şeyler oldu. Pandemide yangında ilk kurtarılacak şeyler olduğu gibi yangında ilk atılacak şeyler de var. Yani bırakıp kaçılacak şeyler var. Pandemide hocalarımız dedi ki, ya ben vermiyordum 302 o zaman pandemide. Ben şimdi online Nyquist anlatamam. Ben de öyle bir şey diyebilirdim yani ben de verseydim. Hayatta bunu online işte bir yandan Zoom'u yapmaya çalışırken bir yandan da Nyquist anlatmaya çalışmak istedim. Öyle bir şey dendi. O yüzden Nyquist atıldı bir dönem veya iki dönem atılmış olabilir. Yani dünya başımıza çökmedi gördüğünüz gibi. Yani herhangi bir şey yaşanmadı. Ama işte o arkadaşlarınızı şöyle problemler bekliyor. Burada doktora yapmak isteyenleri var mı bilmiyorum. Ama doktora yapmak istedikleri takdirde işte bizim doktora yeterlilik sınavlarımızda klasik sorulardan işte Nyquist genellikle doktora yeterlilik sınavında ince yapan, bütün detayları bilinmesi gereken bir şey öyle durumlarda. Veya işte kontrolde daha sonra işte klasik konularda gidip master doktora yapacaksa bir eksikliğini çekebilecek bir şey ama yani kontrol yapmayanları zaten hiç böyle bir şey beklemiyor. So here today's topic is state space methods. The rest of today's topic. So in state space methods, obviously we are using state space equations. X dot is equal to ax plus bu, and y is equal to cx plus du. This is our state space representation. So in general, state space state space representations are actually much more useful when you have multiple input and multiple outputs in your control system. So currently in this course we have only seen single input, single output systems, and this course is going to continue in that respect. But suppose that if a system has 2 inputs and 3 inputs, U1, U2, and U3, okay? And suppose that the system has 2 outputs, Y1 and Y2, okay? Assuming that this is a linear time invariant system, I can actually look at this system in transfer function domain. But when a transfer function is something between a single input and single output, okay? This actually means that I can describe such a system with how many transfer functions? The first transfer function is going to be from U1 to Y1. The second transfer function is going to be from U1 to Y2. The third transfer function is from U2 to Y1 and U2 to Y2. Okay, how many transfer functions will we have in total? 6 transfer functions. So I have to deal with 6 different transfer functions when I try to deal with a multiple input, multiple output system. When you have multiple input, multiple outputs, the state space representations would work in a much better way. Why is that? Because the only thing that is going to change in a MIMO system, multiple input, multiple output system, in the state space representation, what are we going to change? In general, this A is a square matrix, B is a vector, C is a vector, and D is a scalar. If you have multiple input, multiple outputs, what is going to change in these sizes?
Size of C and D.
Yes, size of C, D, and B, they are going to change, and the equations are going to remain the same. I will have exactly the same equations, but the size of B, C, D are going to change when we have multiple input, multiple outputs. Okay? That is why, in general, state space representations would provide us a much better way when we have actually multiple input, multiple output systems. But we have currently 4 plus 1, 5 hours in this course, and we are going to try to give the essence of single input, single output state space systems. We won't see MIMO systems in this course, still single input and single output, and we are going to learn what we can do with state space representations. So here, the first thing that we are going to learn is to convert between state space representations and other representations that we have seen. Okay? So here, let us try to see how we can convert a state space representation into a transfer function representation. In order to be able to obtain a transfer function representation, I need to go into Laplace domain. Okay? G of S is Y of S over U of S. I'm considering again a SISO system, single input, single output system. And here, this is my Laplace transformation or transfer function representation of the system. For a state space system, I can actually calculate what the transfer function is by going into Laplace domain. So I will take the Laplace transformation of both sides. S times x is equal to A times x. I'm assuming that when you calculate a transfer function, you always assume 0 initial conditions. Okay? The Laplace transform of this thing is S times x minus x0. Okay? But transfer function is related to 0 state response. That is why we always assume initial conditions to be equal to 0 when calculating a transfer function. That means that for the Laplace transform of x dot, I can write just S times x. Okay? And I have ax plus b u of s. Because everything is linear here, Laplace transform behaves well. C times x plus d times u. So now what I have to do is I need to get rid of the variables x here. X is a vector, so this is a vector Laplace transformation. So I need to get rid of x. And now biz burada master alırken bir de master interview'ları yapıyoruz. Klasik sorulardan bir tanesi işte state space sistemi buldum. Bana transfer fonksiyonu derive et. Yani işte %50 diyeyim yani. Kimisi tamamıyla yapar ama %50'si birazdan devam edeceğim şekilde devam ediyor. Okay? So you need to find mistakes that I will do here. So I will try to extract x from here. So it is S minus A times X is equal to BU. And then if I extract S here, it is BU divided by S minus A. Then I have Y is equal to C BU S minus A plus DU is equal to, I have C, then I can take U parentheses here. If I take U parentheses, it is CB S minus A plus D. So then this is the transfer function. Okay? Yani bunu dalga geçmek için falan söylemiyorum. Yani sorgulanmadığı zaman böyle oluyor. Öğrenirken sorgulamadığınız zaman bu şekilde oluyor. Ve bu kesinlikle yani transfer fonksiyonu ne bilmeyin. Belki kendimi daha iyi hissederim. Yani o zaman onu bilmediğiniz zaman olmamış, çocuklara göstermemişler veya iyi anlatamamışız derim, tamam mı? Ama böyle olduğu zaman iyice birinci sınıfa kadar inmek gerekiyor. Yani neyle neyi çarpıyorum, neyi neye bölüyorum, neyle neyi topluyorum. Oraya kadar gidiyor. O zaman canım iyice sıkılıyor. So what are the mistakes here?
What is division by a matrix?
Yes, what is that? And is this a matrix? This is a complex scalar, and this is a matrix. Okay? How can I sum them? In MATLAB it sums it, but this is not mathematically defined operation. Okay? So here, this really doesn't make much sense. Okay? So here let us try to do this in a more meaningful way without losing the meaning of every operation. So then here I have S times X and I have A times X. If I take them side by side, it is SX, AX. How can I take S parentheses there? It is going to be Si minus A times X is equal to B times U. And then I need to extract what X is. X is equal to Si minus A inverse times BU, assuming that this matrix is invertible. And then I can substitute this X into Y formula, and it's going to give me C times Si minus A inverse B U plus D U. And then I can take U parentheses here. It is C Si minus A inverse B plus D, and I have U here. And then I can calculate what the transfer function of the system is. It is C times Si minus A inverse B plus D. So now if I look at the sizes of everything here, in this case, C is a horizontal vector, Si minus A is a square matrix, and I have B, which is a vertical vector, and I have D, which is a scalar. Okay? So now we see that this thing would give us a scalar after the multiplication, and I'm summing it with a scalar. Okay? So that is the general transfer function formula you can derive. And here I can actually write the inverse of a matrix in the following form. Let us say that A is equal to A, B, C, D. If this is my matrix, it's a 2 by 2 matrix, and you can actually invert it quite easily. A inverse is, some shortcut here. Change the places, change the signs. It is dA minus B minus C divided by determinant of A. Okay, that is the inverse of the matrix. This type of matrix that you write here has a name in mathematics, and that is called the adjugate matrix of A. Okay, so this is called adjugate of A. Okay, so here, and you can do this type of calculation for any invertible matrix. So if you look at A inverse, you can always write it as the adjugate matrix of A divided by determinant of A. Okay? So now this actually means that I can actually apply this theory to this transfer function. I have a matrix inverse here, so I can write it as the adjugate of Si minus A divided by determinant of A. Okay? So I have G of S is equal to C times adjugate of Si minus A times B divided by determinant of Si minus A plus D. Okay? So I get this one. And now I can equate the denominators. C adjugate Si minus A B plus D divided by, D determinant Si minus A. Divided by determinant Si minus A. Okay. So now here you see something. In the denominator, I have determinant Si minus A. In general, we call this thing as our D of S. Okay? And this is the numerator polynomial, that is n of s. So I can talk about zeros and poles of this transfer function. Zeros are determined by the numerator, and the poles are determined by the denominator. Okay? So I know that poles are in general complex numbers which would make the denominator exactly equal to 0. Okay? So I have determinant Si minus A is equal to 0. The solution of this equation for s's would give me my poles. Okay? So what are the solutions of this equation in terms of the matrix A? Yes. Determinant Si minus A. What is this in terms of for a matrix? In linear algebra, for a matrix, this is a polynomial. It is called the characteristic polynomial of the matrix A. Okay? This is D of S, and it is the characteristic polynomial of A. If I equate this to 0, and if I find the roots for S, I would get the eigenvalues of the matrix A. That actually means that for a system which is for which we have this state space representation, the poles are going to be eigenvalues of the matrix A. Okay? So in general, if we are talking about a state space representation of a system, if I ask you the poles, then what you have to do is to find the eigenvalues of the matrix A. So I have poles are eigenvalues of A. So now we have learned how to pass from state space representations into transfer function representations. Okay? So now we are going to learn the reverse transformation. So from transfer function into state space representations. Okay? So given a transfer function, we are actually going to be able to find important state space representations that we are going to consider. Given a single transfer function, how many state space representations I can find for a transfer function? Infinitely many. And these would depend on our state selection. So depending on our state variable selection, we can find infinitely many different state space representations for a single transfer function. In this part of the course, we are going to learn only 3 specific ones that we are going to consider in the rest of the course in these 2 weeks. So these are going to be called diagonal canonical form. Canonical. Canonical means standard in some way. Canonical form. And we will learn something called controllable canonical form. And we will learn something called observable canonical form. These are going to be 3 important state space representations that we are going to learn in this part of the course. So here I will give you a general form of transfer function. G of s is going to be equal to b1s to the n minus 1 plus b2s to the n minus 2 going until bn. Okay? Divided by s to the n plus a1s to the n minus 1, going until an here. Okay? This is the general form of transfer functions that we are going to consider. I will call this n of s, and I will call the denominator as d of s. The first thing that I'm going to consider is whether this is a loss of generality or not. What type of restrictions do we have in this transfer function that I have written? This is the general transfer function that we will use. What type of generality would I lose with this transfer function? First of all, the order of the numerator is actually strictly smaller than the order of the denominator. Okay? Then what would happen if I have equal orders in both the numerator and the denominator? Let us have such a transfer function, 2s squared plus 3s plus 4 divided by s squared plus 2s plus 3. If I have such a transfer function, how can I apply this theory, this type of general theory to this?
1 plus something.
Yes, I will just separate the part of the transfer function which is bringing us a constant component. So I will have here the following: 2, I will have s squared plus 2s plus 3 here, okay? And then this is going to give me 2s squared plus 4s, so I will subtract minus s, plus 6, and I will subtract minus 2 here, okay? Then I have s squared plus 2s plus 3. This is going to be 2, and I can take minus s plus 2 divided by s squared plus 2s plus 3 plus 2. Okay? So here, now look at this thing. Okay? So when I look at such a transfer function, this is going to be C si minus a inverse b plus d. Okay? So here, this 2 here is just going to be equal to 2 in that case. Okay? And ABC will be determined, ABC will be determined by this part, which is in that form. Okay? And D is just going to be equal to 2 in that case. Okay? So here, when we start with such a transfer function, we are assuming that if the transfer function has equal orders in the numerator and the denominator, we assume that constant input gain, is separated from it, and I can place it instead of A. Okay? And the rest I can use the theory that we are going to learn in this part. Here, another restriction might be, for example, the coefficient of the largest order term in the denominator is 1. Is that a loss of generality? For example, if I have s plus 1 plus 2s squared plus 3s plus 4. Will this theory apply to this transfer function? How? I will just take two parentheses here. Okay, this is 1 over 2 s plus 1 divided by s squared plus 3 over 2s plus 2. Okay, in this case, we see that, so here, I can always assume that the largest order coefficient of the denominator is actually equal to 1 without loss of generality. Okay? So here, as we see, we can cover all cases with this type of theory. The first transfer function, the first state space representation that we are going to learn is going to be called diagonal canonical form. And in this case, we are going to have an assumption. Roots of d of s are distinct. Okay? This is going to be the assumption that we are going to use in deriving the diagonal canonical form. Okay? This means that when I look at the denominator there, d of s is looking like this: s minus p1, s minus p2, going until s minus pn here. Okay? And I will say that pi is not equal to pj for I not equal to j. Okay? I am assuming distinct roots here. Okay? So when you have some repeated roots in the denominator, sometimes diagonal canonical form of a transfer function, state space representation, might not exist. Okay? In this case, we are going to see that this A matrix, when we obtain the state space representation, A matrix is going to be a diagonal matrix. Okay? But for some d of s polynomials with repeated roots, we will not be able to obtain a diagonal canonical form state space representation. So here let us try to derive the diagonal canonical form state space representation. I know that I have g of s given like this. I have b1 s to the n minus 1 going until bn divided by s minus p1, s minus p2 going until s minus pn. I have such a transfer function. And if I would like to calculate the output, then what I can do here is that I can apply partial fraction expansion to this g of s, okay? And I can obtain here I from 1 to n. I can apply a partial fraction expansion to there. It is going to be s minus pi and alpha I coefficients here. In this equality, I'm making this assumption, okay? Because if some of the poles are repeated, then my partial fraction expansion might not look like this, okay? So that assumption is actually used here in this equality, okay? So I know that y of s is equal to g of s times u of s, okay? And if I use that form of u of s instead of g of s, I will obtain this. I will have I from 1 to n, alpha I, u of s, divided by s minus pi. Buna partial fraction expansion yaptım ve partial fraction expansion'ın koefficientları. Yani işte s artı 1 bölü s artı 2, s artı 3 diye bir şey varsa bunu a bölü s artı 2 artı b bölü s artı 3 olarak yazdım. A'ya ve b'ye alfa 1, alfa 2 dedim. Okay. So now I have these quantities. In diagonal canonical form, we are going to select our states xi in Laplace domain by using the following formula. So I will have alpha I, so I will choose these elements as my state variable Laplace transforms. Alpha I u of s, s minus pi. Okay? So then, selecting these as my state variables, maybe I should remove these alphas from here. So this is going to be my selection, and we see that y of s in that case is going to be I from 1 to n alpha I times xi. Okay? I define my state variables in this form. Okay? When I define my state variables in this form, this is going to be my output, a linear combination of the state variables. Okay? So now I will look at that state equation. That state equation tells us that s minus pi x of s is equal to u of s. Okay? And when I distribute this, I will get s times x is equal to pi times x. I will have xi here. And u of s. Okay. This is the state equation in Laplace domain. Alright? Now if I convert this equation into time domain, what am I going to get? Instead of s times xi, what should I write? xi dot is equal to pi times xi plus u. Okay? This is the equation for the ith state variable. Okay? When I try to write this state space representation, for the first state variable, x1 dot is going to be p1 x1 plus u. So what is going to be my A matrix? I need to write x1 dot is equal to p1 times x1 plus u. Okay? What should I choose my first row of the A matrix for satisfying that equation?
P1, 0.
P1, 0, and all zeros. And here, 1. And the second equation is x2 dot is equal to p2x2 plus u. And the second row is going to be 0, p2, and I will have all zeros. And these are all going to continue actually until pn here. Okay, I will have zeros everywhere else. And I will have ones here. And what should I choose these coefficients? Y is going to be written in terms of the state variables with the alpha coefficients. So I will have alpha 1, alpha 2, going until alpha n. So this is called the diagonal canonical form, state space representation. And we will solve some examples in this respect in the next lecture. That's all for today. Thank you very much.
Burada sadece tek bir pi aynı, sadece bir değer aynı anda sıfır